Thank you very much, Paula. It's a real honor to be here. The idea of coming to a Center for Place and Memory is perfect for me. A whole career is spent thinking about place and memory, so I could not be in a better place to give a talk. Welcome to everyone online. Hopefully you can hear me well there. And so, yeah, without further ado, I'll start talking about the research we've been doing on navigation in cities and on the ocean. I'll start with a reflection of how I really got into the depth of where I am now is thanks to this amazing scientist, Eleanor Maguire, who sadly passed away at the start of this year. And she'd had a glittering career, dragged me into her lab to do things. And so she was an Irish neuroscientist at University College London, a fellow of the Royal Society, most famous for her discovery that the posterior part of taxi drivers' brains in London grows larger, which is also, and she won the Ig Nobel Prize for this. But actually, her real foundation was just pushing the boundaries of what it was possible to do with naturalistic stimuli. That is where Eleanor will kind of go, and her work on scene construction, hundreds of other topics. But for me, she was the person that said, come into my lab and start working with London taxi drivers. So I really, yeah, I'd like to really thank. I have very, very fond memories of Eleanor. It's very sad she's not here, but this is a memory. That was a formal picture of her in an obituary. Top left of this screen you're looking at is Eleanor as well, the back of her head. And that is in the scanning room, a very densely packed technical room in the brain imaging laboratory of central London, where SPM was designed and built by the team there. And I'm there in a grey shirt and a tie. We all wore ties to do research back in 2000 or so. Darsh Kumaran is the person, right? So what his position now is in DeepMind, but he was one of the founding members of DeepMind, the program. And Demis Hassabis, off camera somewhere, is the owner of DeepMind, who was part of our lab back then. What we were doing there in this naturalistic experiment, studying navigation in cities, was that we co-opted in a £4 million video game called The Getaway, which took the team £2 million to recreate London in virtual reality back then in 2004. You can see some of the footage in one of the screens of a taxi driving through a street of London. And this is like, this was really Eleanor Maguire, like driving, saying, we can do this. I just wouldn't believe it. And hopefully you'll see at the end of the talk is kind of, because she gave me the belief you can do crazy things, we've sort of followed that. So in the bottom left of that image is an MRI scanner that's lethal for anyone who's got metal in them or anybody carrying metal with them. Next to it is a game controller, a Sony game controller, which would kill anyone who was actually using a real one. But that one was a custom-built, entirely metal-free game controller, probably cost about £30,000 to build it from scratch there. But we used that to allow London taxi drivers, the ones with the larger hippocampus, to drive through this £4 million simulation and tell us about what they were thinking as they did so. So here's a kind of picture of a view in London that's taken from the game. So a really busy Trafalgar Square, driving around with really annoying traffic and people jumping out in front of you like the real London. And what we found back then in 2006 was that when taxi drivers afterwards, eating biscuits and looking at a film review, told us they were thinking certain thoughts, we could see bits of the brain like the hippocampus particularly active when they were thinking about things like the route ahead for them. So that's really how I got into this madness I'm going to talk about. And by madness, I mean the challenges of actually running field work that's got neuroscience in it is a challenge. That was how I got in. And here are now many of the collaborators who I work with. And these are some of the people whose work I'll mention in the talk. I'm just going to show the gallery of the team who are involved in lots of different, many of these people pop up across projects. Top right is Pablo Fernandez Velasco, who's sitting in the middle of the room, who is a member of the center here for Place and Memory. And we'll feature in the end of today's, he'll be in some videos at the end. He's not looking forward to that. And then other bits and members of the team, various PhD students and senior collaborators and so on. I'm going to start with the top left. The two very key people in my career are Michael Hornberger and Antoine Coutreau. Michael and I were collaborating. He's a dementia researcher. His whole career is around Alzheimer's disease and other dementias. And we were collaborating on, could we build a video game to help identify people with Alzheimer's? And we've got very little skill in that. But one day, Michael got an email saying, oh, somebody'd like to fund an idea around dementia, but for a sort of public-facing entity. Would you be interested? And together we put in a one-pager they wanted. We just want one page, submitted it. A while later, we got an email that said, great, you've been picked. congrats. For what? We didn't know exactly what we'd signed up to. And then they told us, oh, it's a company that undisclosed until you sign a long NDA, and they've got infinite amount of money. And it wasn't infinite. It wasn't an infinite amount of money, but it was towards £12 million to run a study. And that's how, as Paula introduced, how did we get to 4 million people recruited? A lot of that requires advertising, big advertising budgets. But that's what any huge company needs to do. And this company, in this case, was Deutsche Telekom, who decided to take one of their advertising campaigns and put it into philanthropy and try and help us to build a video game. And the most exciting thing about that project was they took a substantial sum of money and put it into a commercial games company. I could never apply to the UK government or a large funder to say, look, we want to spend £1 million on a games company and we need like many millions for advertising. It's just impossible. So luckily we were able to hire in a company called Glitchers, who are an incredible Scottish company. They weren't then, but they're now based in Edinburgh. And they were just the most compelling of all the many giant companies at that time. They were a new startup company then, had just started. But they built a game called See Hero Quest with us. And it was a real collaboration. A lot of my ideas for science, they just told me were nonsense. Like that, they were never going to work, in that we wanted a test, a valid navigation test, online on App Store and Google Play that anyone would download. And if we made this game, this test, too boring, 5 people will sign up and their business will be ruined. So they were not going to let anything that wasn't exciting and engaging work, or anything that was going to make people vomit, which is what you'll get in a lot of standardized tests if they're not done well. And so Glitchers, the team, with the genius idea to me they came up with was, let's put people on boats. One of the company wanted dinosaurs on quad bikes. I decided not to go for that. Another one was like a terrifying ghosts chasing, trying to kill you and murder you. We just also didn't think that was going to work. But they had the idea of boats on a quest in the ocean and through all sorts of aquatic environments. They wanted to track down and kill sea creatures. The charity stepped in and said, we're not killing any Arctic sea creatures. So they turned the whole game into photographing and building a catalog of photographs of these sea monsters. I'll show you a clip of playing the game now. So this is See Hero Quest. There's 75 levels in this game. This is the supplementary material from our first paper. I'll just pause it if I can. When you start the game, this is level 8. So you've got 7 levels before this of this game to kind of get used to the controls. But you play it on a phone or a tablet or anything that's got a touch screen. You can also play it on a Mac. It'll run fine. Basic idea was, let's do kind of orienteering. You get a nautical map. Here's where you are. Here's where you need to get to these checkpoints, and memorize it, put it away, and now try and find those places. So that's map number 8, and it's a bit fuzzed out. Some maps are completely destroyed by water damage on purpose. Others are crystal clear. There's a lot of manipulations with the environment. So people click close, the little boat appears, and they can tap on the screen to guide this boat around. And this is Antoine, who's the first author on the paper guiding the boat very accurately. But thank goodness people were not all fantastic, because in psychology, you need lots of errors. You need people to screw things up to learn how the human mind works. And here, as this person is playing this, the whole time they're doing it on their phone, it's logging the coordinates of that boat in the virtual world. So this is a very efficient route. And because of the marketing and the advertising, and it's a game, it tells you, amazing, you nailed it. And it encourages you to do more. I'll pause that there. Hold on a minute. But yeah, it logged all that data locally, sends it to a server. We've got 4 million people across 195 countries to do this. And of course, we don't know how valid they all are. We know 600 people from the Vatican signed up, and there's only 350 registered there. So we know the kind of range of like faking of data. There's a whole paper with Pablo where we looked at some of this faking, but generally with 4 million people, we're pretty happy. We've done a lot of robustness checks on it. But with that journey that person did in that one level, that was a very good navigator. The distance was short. We can look at that with lots and lots of people and then understand how that varies. So what I will show you next is a diagram, is a map. And here's some other images just to show, we had tropical islands, we had rolling seas, we had marshes. It was a fully immersive kind of fun game. And you capture these sea monsters. Simon Vukoviak, who was in our team a while ago with that, manly created this nice animation where instead of 4 million people, we're just going to show you 101. There's 101 all superimposed. These little blue dots, they're not doing it together. It's not a group. We'll put everyone's data all over the top of each other and see how 100 people would do if they were all plotted. And you can see there are people in the lead, people right at the end, people going backwards. As this progresses on, I'll jump ahead. You'll see it gets very chaotic, and by the middle, it's just pinball rolling around. It's just chaos. Important in this diagram is one of those dots is red. That person, the person who's a red dot, gets lost every single day in the place they've worked for decades. They cannot find their way. They're one of a large group of people. I mean, relatively, it's not large, but there's a substantive number of people who really find it hard navigating. And this person has a medical condition, and they were born with hydrocephalus. So it's also exacerbated that problem. But as we watch this, they're not doing very well. But if we go towards the end, sadly, it's pretty much the red dot. As we go forward, it really is just the red dot. That person really struggles to find their way out of the dead end and get to the end point. So that's all very well. But the key with SeaRequest, once you've got 4 million people, you can titrate down. Those 100 people are exactly matched for age, gender, background, education, how fast they are, everything. So that when you look at that diversity of that population, we can be pretty confident that person really is an outlier relative to their mean. We publish a lot of papers. I'm not going to go through all the data today because I'd rather talk about other things we've been doing in cities, but there's a lot of things we discovered using it, like how much sleep is important. Age is very important. So as we get older, our navigation skill declines. That's not surprising from other cognition, but it declines faster than we'd anticipated. But I thought this was a particularly interesting feature, is where in the world do you find the best navigators? Because we have 195 countries, we can ask that question, and we can do it systematically where we run linear models, where you can equate, So if you just take the raw scores, Sweden wins. Sweden has the best navigators in the world, but a lot of young men took part, and a lot of young men who play a lot of video games at that point may have biased the data. So the actual winners, if you look at the chart, are the Finnish people, to the annoyance of the Swedes, who nearly won. So the Finnish turn out to have the highest navigation skill, but Norway and Sweden, there's very little difference between these Nordic countries. And when we first reported this, new scientists went, Viking blood, it's got to be the Vikings. And a lot of people then said, no, I don't think it's the Vikings. More likely, in fact, it's the fact that in those countries, in these countries, you go to school and you get trained on how to navigate. At school, they do orienteering lessons. I grew up in Scotland. I'm pointing here because I'm in Scotland. And we did country dancing. So if there was some sort of test online, maybe that would help if you've grown up in Scotland. But everyone should probably get this skill. In fact, because of this kind of narrative, we then looked at each of those countries plus 13 in total countries do compete with each other for an orienteering championships. They go to somewhere internationally, teams compete, and each country's got a medals haul over time. So, Finland's very high on that list, and other countries are very good. UK's middle, and I forget who's the worst, I won't say. But we could show with a very strong correlation that you could predict that medals haul from SeaRequest. So countries that do the best in this tend to do the best in the real world. So it's a very small sample of countries, but evidence of ecological validity. We also showed, and I'm going to show it here, one of these papers, and Pablo's on one of the papers too, where both younger and older people, when they play SeaRequest, you can use that to predict being lost in London or in Paris. So we've tested this game does actually do what we intended. It actually tracks real world getting lost. But the most interesting thing we found was really in relation to this question, which gave us a big shock when we looked at the data. We're only able to ask really 9 questions of any sense because of the international nature of it. Whenever anybody came up with a question, it was kind of like, how are we going to translate that to Finnish or to some other country with clarity? But one that was very clear was, do you live in a city or outside a city or some mix? And so I was always curious here. I've kind of illustrated cities are very dense places with lots of landmarks and lots of paths, and it can be confusing. But on the other hand, rural environments, like out there in the hills from Stirling, you go big distances and you got to keep track of where you're going. They both present challenges. Is there an advantage of growing up in one over the other? And what we did find an effect. So what I'm going to now show you is on the y-axis of this graph is wayfinding performance from our game. So the video you saw earlier of the boat moving, that's someone very high. They'd score like a 2 on this scale. On the y-axis is age, from like 19 years right up to 70 years, where we're confident about the data. And you're not going to be surprised to see that as people get older, their ability to solve this high-action video game navigation task declines. And that's what we see across these 4 lines. And what we stratified that data into is people who are male or female. So there is a male advantage around the world, which is very small, I should say, in those Scandinavian countries. And I'll get back to that maybe. But in green and gray, we're looking at outside cities in green versus inside cities in gray. What you see in that gray, let me unpack that, is that although there's a age effect and there's a gender effect, there's quite a substantive effect that's beneficial growing up outside cities. And in fact, if you look at the graph carefully, a woman who grew up inside a city in her 60s is equivalent to a woman who grew up outside a city in her 70s. So that's a 10-year advantage in skill growing up inside cities. And this was universally average around the world. And we were wondering why. I remember Antoine, who I showed a photograph of him earlier, really deserves big credit. He's the first author on the paper, for thinking, I wonder if we can pull out, is it, first of all, when we look at the data, it's not uniform. Like Ireland, there's very little effect. Romania almost goes the other direction. It's better growing up in Romanian cities. And if anybody's been to Romania and the cities there, you might start to think why. Because what we discovered was that it did matter how organized or disorganized the city street networks were in countries. And there's a chap called Jeff Boeing, just around the time we were looking at our data, who's a geographer, who put out a paper in Applied Network Science showing you could quantify every city in the world into how organized or disorganized it is, creating something called the street network entropy measure. He just calculates how aligned all the streets are. So Prague is pretty misaligned. Chicago, boy, is very aligned. I think Toronto is one of the most aligned cities in the world, for example. And here's one of his big figures. He's drawn out. So top left is Chicago, I think, or something like that. It's hard to read for me. The bottom right is Sao Paulo and Rome, where it's just, there is no organization. You know, Rome is a fantastic city, and part of the joy of Rome may be that it is disorganized in some way, at least to me as a non-Roman. I'm telling all of this because the key discovery we made, that's the center point of this paper we published, is that there's what we found, and we plotted that street network entropy. So Chicago is down here on this graph, and Prague is sort of up here somewhere, and Rome is right at the top. We took all of the cities for every country we had data from, worked out, say, for Italy, how averagely complicated are their, windy are their streets. For USA, how gritty or windy are they? And that's what we're going to plot. And against it, we're going to put in the environment effect size. So the further to the right on this y-axis or x-axis, the further you are over to the right, the bigger the gap, the bigger the advantage going up outside cities. And I'm showing that because we found a striking negative correlation that the more gritty the streets were, like in Argentina, in the cities, the worse it is growing up in a Argentinian, for example, or United States or Canadian city compared to the outside. Whereas countries like Albania, Romania, Ireland, there is very little effect. It's still there, but it's much, much smaller effect of cities. After we published papers, somebody did send me a handwritten note to say, I think you're wrong. This paper in Nature is wrong. It's fluoride. It's not the grittiness. We didn't check on the fluoride content, so we can't rule it out, but I suspect it's more likely it's the grittiness. And there's a lot of data packed in there. We had 5 reviewers, and they gave us a lot of tasks to do that were helpful in many cases. But we replicated the effect. So, for example, we rebuilt something called the City Hero Quest. We showed it's not just aquatic adventures. So it's not that we test the people in a rural environment and they have a benefit. People are just as bad when you give them a virtual car, for example. And we could refine the exact same effect in a new sample. So there's a lot packed into that Nature paper, but the main upshot is that the environment you grow up in, the structure of it can profoundly affect your navigation skill, giving someone a 10-year advantage potentially. Crucially, the title of the paper is "Cities are bad for you" was not the title we ended up with, and that's because there was a slight advantage of people who grew up in gritty cities navigating gritty environments. So it seems more like, so if you had someone from Dublin or Buenos Aires and you go to New York, use the New Yorker to kind of help you find your way. Sorry, the Buenos Aires person going to New York, because they've grown up in a very gritty city. Their brain is attuned to grittiness. So we found these effects that I'll move on from. But yeah, really quite profound effects of the environment, and yeah, something we need to really think about when we design cities. I'm now going to move from the virtual world to the dirty real world, where there's not clean virtual spaces, but the dirty streets of London, in fact. And I'm going to present this man. This is Graham Greenlass. He is a London licensed taxi driver. Around his neck, if you look carefully, is a little badge, a little golden badge with green around it. And he has a green badge license to drive the whole of London. And he will have spent 2 to 4 years training his brain to get that badge and to charge people a substantive sum of money to jump in his black cab. And he is one of many, many thousands of London black cab drivers who, since the 1840s, have had a parliamentary act to say they needed to get this knowledge of the London streets. And Eleanor Maguire, as I started, found that his brain and others like it will be larger in the posterior part of his hippocampus. And it's something we're retesting in our lab now. We're going back with modern, more advanced imaging methods to try and track that and also look at the functional consequences of it. And I can't say yet because we haven't finished collecting the data. What I am going to present, though, is the fun thing about London taxi drivers for scientists like me is that they are systematic. If we took everyone in this room and wanted to test them on Stirling, there might be bits they know and bits they don't know of Stirling, and it becomes a bit of a mishmash. You can guarantee, because he's been through a test, that Graham, like some guy called John and Joe, whoever's got this license, they know London. And if you test them, they can do it. So what we set out to do with a student, Ava Gracebauer, in the lab was to get taxi drivers to describe taking routes through London in exactly the way they do in their exam. So they, when they go into this public carriage office to get that green badge, are given this. The examiner will sit them down and say, "Okay, tell me all the streets between Paddington Station and Elephant Castle." And if they get any one of those wrong, they laugh and send them out the door. So it takes 16, I'm asking like 24 times of going into that office and being probed on those street names. And what you're seeing in this little animation, each of those little dots is a real-time description of like each of the streets between somewhere in north of this is High Park here, somewhere north of High Park, and they do have to get down to somewhere in South London. And these taxi drivers are describing each of the streets. Like some of them snake their way through the middle of the park and others. So that was our test, was we'll go into the street, we'll give them some cash, and they in return will describe, when we give them a start and end point, all the streets. And almost no Londoners would be able to do this, but Graham and others like him, it's just like, oh yeah, just what, like the exam? Yeah, the exam. If you put that data together, you get a pattern like this, where you can connect up all the dots, all the streets, and you can put circles on this map are the delay it takes them to think about it. Unsurprisingly, there's a big circle when they first are presented with the challenge. So there's a kind of initial planning moment where they think, okay, how am I going to do this? And it's worth thinking, these guys get really, and women, there's a really increasing number of women who are doing this. It used to be very male dominated and has shifted, which is also a very good thing. But they haven't got long, got 3 seconds to solve that, because they'll have all these people honking behind them on Euston Road saying, can't just sit there, you've got to go. And it's costing the customer time. So they are quick. The average time to describe each street is 1.8 seconds. And most of the time they just rattle through, there's almost no gap. But it's the gaps we were interested in, how long they're taking to think about their next street. And so we took the data from all these, we did 16 routes and 40 taxi drivers, and we put it all into a linear model where we can say we want to predict that the length of time it takes them to describe the next step in the street network. What matters? What parameters matter? An obvious one would be how far. Like if it's just the next couple of streets, they should be quick. If it's the whole of blimmin' London to get across, that's quite a long route. They should be quite slow. So we can look at the distance, we can look at whether they have to turn, we can look at lots of parameters. Do they like going to South London? It's a joke about taxi drivers not wanting to go to South London because they'll lose money down there. There's less places to get customers, but we didn't find that. What we did find in this graph, so the axis here up in the y-axis is saying If it goes up, it means they're slow. Their reaction times, the log of the reaction times in this model, if it's high, they're slow. If it's down, it's fast. So what we found the biggest effect with 3 dots above it was that if they have to turn in their description through the space, they're slow. They all get slowed by this. And it's useful to think they always have to describe the direction. So it's not like they're adding another word of left or right. They always have to say forward and to right and to, so they're always prefacing the direction they travel. But still there's this delay, which may be evidence of an embodiment potentially, in that they have to actually, in their mind's eye, turn, and it just slows them down. Or it could be computationally that requires more processing. It's not embodiment. Main roads slow them. Surprisingly, if you hit Oxford Street and you're thinking, what are all the ways I can go from Oxford Street? They're slow. Distance had almost no effect. That little line to the right, almost nothing. And I think that's because they hierarchically compress. They don't search through the whole of 26,000 streets doing a big search in their head, because that's more options than there are stars in our galaxy. It's billions of options. So they don't do that. They know what they're doing. They hierarchically compress. And so distance doesn't really matter. What was fascinating, though, was that if they land on a boundary between certain neighborhoods, they'll be faster. And this was something we predicted, because they really learn about these boundaries to exploit. If you're going to hierarchically plan London, you think, let's get to Soho. In Soho, I'll do what I need to do, but let me get to Soho first. So what we're showing there is if they land on the boundary for Soho, a very clear region of London, they will be quicker. And our assumption is they pre-planned that. So that's just looking at the surface features. But what we were able to do, and Pablo joined the team working with a scientist, Daniel McNamee, at this point, was to dig deeper, start applying mathematical models, because that image on the left, it's a map of London, but it's also a graph. It's a graph with nodes and connections. And if it's a graph with nodes and connections, you can start applying graph theory, and you can start asking about what mathematically is it about the planning process in a graph that matters. If you've got to go and put together a piece of IKEA furniture, it's the same as a graph of possible ways you can connect a piece of IKEA furniture together. So this is an idea of something general with planning we're now looking at, more than just turning. And the diagram there, the actual key, is many bits of data in our paper in PNS we published at the start of this year. What was intriguing in the data was it did matter how long they started thinking at the start. So some taxi drivers would quickly get into describing the route. Others would like scratch their head and think a bit. And that just might be thinking. What we actually found was that when you dissect apart the choices they then make, we found that the streets that have this high transition entropy, so when you land in a bit of London on a certain street, if there are many options and there's a real diversity of ways you might be able to travel from that through the network, it's more complex. It's slower to do that. But what we found is they substantially speed up on those streets. That's this drop in lines, the significant effect, if they thought about it ahead of time. And that's what mathematically they describe in the reinforcement learning field as pre-caching. You have a complicated decision tree you've got to plan through. And if you're able to solve the tricky bits ahead of time, then you pre-cache some planning. So the importance of what I'm saying is that we've gone out into the street, handed some guys some cash, got them to describe things, but ultimately be able to take that and start to understand the actual human planning process in a complex, very big network of possibilities. But you could apply this to anything else, building an airplane or planning a wedding or whatever you want to look at that could be decomposed. So that's taxi drivers, that's them with their behavior. And then go back to a study we did before, just to highlight our work on looking at cities where we use brain imaging to understand not just the choices people make, but what is happening inside their head when they are planning routes, navigating London. So for this next study, it's quite a nice image from our paper in Nature Communications a while ago with Amir Javadi, where we took a team of the architecture department at UCL. I've formed strong relationships I'll show in a moment, where they were able to take the streets of London and decompose them into graph theoretic measures. In this case, they've reshown every street in central London, with red being streets that have high closeness centrality. In graph theory, closeness centrality is how centrally connected to the middle of the network is a given node, or in this case, a street in the graph. So Oxford Street is highly, highly connected to all the other streets locally in London. Seven Dials is also all these streets in central London, but there are some dead ends that are less connected. And once you get to South London, you're further away. Another measure is betweenness centrality. So in betweenness centrality is how often you would tend to go through that street if you were going from any one place to another. So taxi drivers would go through these red streets a lot, in theory. Bridges, for example, are very red because you have to go over them if you want to get from south to north across the river. So this is another network measure. These are global measures. You can also measure just the local connectivity. Like if I step into Seven Dials, options. If I go to Duck Lane, there's one. You're in Duck Lane, you've got to get out of it. And it's pretty grim, to be honest. It's a back street in Soho. And the little white line, talking of Soho, is where we ran our study. So the whole of London, we can't scan people's brains exploring the whole of London. But what we did was take, I think it was 24 participants who were naive to Soho, maybe been there once or twice, took them there on a 3-hour guided tour. They had to learn in a very particular to where are all these, like, where's Ronnie Scott's jazz bar? Where's the local, corner shop? Where's this bar, cafe? And Soho is fantastic for two reasons. One, it's full of landmarks. You really, when you see a photograph, you can quickly go, oh yeah, that's Brewer Street. And the second thing is that if you want to test people in the scanner later, which is what we did with videos, you can show someone a video of a route through Soho, and within 30 seconds, they may have made 5 choices. Because the street, you could easily have 3 streets in this room, because Soho is just so old and dense. So as a scientist, it's great. It's not like Bloomsbury. So what did we do? So we did that. We trained people. We put them in the MRI scanner the day after they passed the test, like a London taxi driver. And we showed them movies we'd shot first person with a film crew. So they watched these movies. They took novel routes. So they'd never taken the exact route this was taking. And we recorded their brain activity. What we did then was measure for all those routes those graph theoretic measures. So here, this diagram, you can see in red is some streets that are highly connected, in yellow ones that are less connected. And if we had dead ends, they'd be even less connected. So as someone goes on a journey through our movies, they were either being told with the sat nav what route to take. That's our control condition. They don't have to think. Or they had to choose, do I go left or right? If they made the right choices, they came away with more money. So they're motivated to make the right choices in this. And what we can look at is their brain activity at each moment on that journey through the route to see what's happening. And what we found was particularly the moments they step into a new street. So if you're going through Soho and you turn a corner and you now see, say, Brewer Street, if Brewer Street has many connections to it, there'll be more activity in the posterior right hippocampus, which is the area shown here. And that is precisely the bit of the brain that Eleanor Maguire identified in the year 2000 that was larger in people like Graham Greenlass. So this is this particular bit. Because of the way we designed the study, we could start interrogating and finding out more about that response. When we look at our sat-nav condition, the control condition in this graph con, there's nothing. So if you are just being told which way to go, there is no response in your hippocampus to the complexity of the street network. You have to be thinking about your route to find this pattern. And we found that if you looked at the difference between those, it really was just the hippocampus and the posterior part that responded. It was also only really interested in local connections, not the global connections in Soho. So it's responding to what you can do immediately. Final thing on this that I think is important when you go into things like neuroarchitecture or neurourbanism, 2 fields that are growing, is that we can also pin down when is it responding. So it responds to the street connectivity. But what this diagram, this is an axiometric projection of the houses in Soho, is that it doesn't care when you're making decisions and it doesn't care when you're walking down in the movie down the street. It's that brief moment of reveal. There's something new here that the hippocampus gets excited. And as I said, it is getting less excited if it's a dead end. There are other bits of your brain that probably get excited in dead ends, but that wasn't the focus we looked at here. So I'm going to now move from here. We're going to be showing you now movies. So this is a paper where it's just coming out in the Journal of Cognitive Neuroscience, the brain imaging side of this, where we thought, let's go back and do that Soho study again with film. It's just this time, let's show people complex or simple spaces they've never been to before, but mix that up with aesthetics, because Soho is, it's full of very glaring things. It's pretty homogeneous. We wanted to see if the bits of the brain like the hippocampus and other parts of the brain, like the prefrontal cortex and possibly the amygdala and others, where are the bits of the brain that actually are interested in the aesthetic experience of space? Now, what I'm showing you here are two movies, and they're snippets of YouTube movies we found that people saw in the brain scanner. They were having to either judge these movies, counterbalanced across a group of subjects, for, do you like this space? At the end, on a scale of 1 to 5. And I probably, if I was watching it, would think, oh, no, I'm not sure I like the top one and the bottom one maybe a bit more, but they're not the most amazing places I would ever encounter. And there might be some movies we found where actually we did a big search for 6 months and it was appallingly awful places we could put on camera that weren't, I mean, there were some we cut out. You know, we didn't want dead cats appearing in the movies, but we had really, these don't fully capture the full grimness of some of the worst. And some of the best were kind of, holiday resorts where people pay a lot of money to go to these places. But here I'm focusing on the complexity. So although that they are visually complicated, both of these movies, the bottom one is in fact actually, the layout is super simple. There's just 2 rooms. The top one, there's no end of places you are moving around. So we're interested in, is there a bit of the brain or bits of the brain that respond to the structure of the environment? And indeed, unsurprisingly, we found the hippocampus and the parahippocampus and a set of other brain areas well associated with spatial and everything did indeed exactly pull out the complexity of the environment. This was not a surprise. What was to us more interesting was, let's go back. I jumped ahead a bit, maybe. Oh no, I have jumped. I have missed something out. So we did find, it's not shown here, when you get to the aesthetics, that the prefrontal cortex now was more interested, the medial orbital region. This is a bit of the brain that responds if you give people like their favorite smell or suddenly reward them with £50 or show them some image they really like, it will universally respond. And we saw the same thing for the architecture and the spaces. This is a bit where we're showing people a 3-second clip and saying, can you tell me everything that happened in this movie? And when they could not remember it, some of the movies they could not remember at all, and others they could remember. And the simpler positive spaces tend to be better remembered. And crucially, specifically, the hippocampus and parahippocampus are more active in those spaces people are remembered. So this is the first kind of, what we're aware of, evidence of brain activity encoding spaces, not just photographs or scenes. Okay, so that's work we've been doing on kind of trying to get the aesthetics and complexity of spaces using brain imaging. But people aren't actually there. They're like you, they're sitting watching a movie. And you can do things with that, but you're not physically there. You're not going to hit anybody. There's no social embarrassment lying in an MRI scanner. The world is full of people and complexity, just like now I'm in a room with a group of people and I'm on stage. More so, let's take Piccadilly Circus. If you step into Piccadilly Circus most of the time, you are surrounded by people around you, swirling around. And just like the study I've shown you, most of the previous ones, the research in the field I work in has really worked on ghost towns, virtual reality ghost towns, or if it is, it's like we shot our movies in Soho at 5 in the morning because we didn't want people walking up to the camera and smiling into it. So how to get at this? And the approach we took with this was to use the Pearl Laboratory in London. So this is a £50 million engineering facility. It looks like this inside. And inside Pearl, we're very fortunate to use money from the Higher Education Innovation Fund, which is there to allow academics in the UK to reach out to industry. You're not allowed to use it for research costs. So we ran an exciting innovation day to show innovators, and by accident happened to collect a whole lot of very valuable data. We built an entire one-to-one art gallery that we could control. So this is Becky Inster, who's the head of the production team there from the world of theatre. We put together a wall of curtains. There's 12 different rooms with 12 different virtual displays, showing, as in TV displays, showing artwork. And then we invited 102 people, put on QR-coded caps because we wanted to record their head position from a whole array of cameras in the ceiling. And they walk through this space we created. And what we did on the day, I'll show you some more footage of them. Some of them were instrumented with EEG systems. Some of them had activity trackers, and 7 of them had eye trackers on. I'll show you some of that. Because it's a psychology experiment, they also filled out a ton of clipboards, questionnaires about their lives. And this actually is the big thing here, because people will tell you, oh, there's tons of data out there on crowds. Just look at the BBC footage recently of the incredibly sad killing of somebody. There's crowds moving and you can study that. But did they ask everyone in the crowd about their background? And did they all physically consent in a consent form to have their data analyzed? No, not really. But in this case, we were very carefully able to get everyone's full consent and lots of questions about their background and how they felt about what we did to them. What we did to them was to put them into a maze. I'm going to show you some eye tracking from the one of our eye trackers, the Toby one, or what it's like inside this experiment. And there we go. Go forward.
Okay.
We'll just put the audio out. Hopefully you can hear me. Yeah, I hope you were on the audio. And if people were given this, you can see what it's like in the crowd in there. We created a really crowded space with 100 people. You were constantly knocking into people trying to get around the space. They had 20 minutes to explore the space, and then they opened an envelope that had a sequence of numbers in it, and those numbers corresponded to those pieces of artwork. Everyone had a totally unique combination of numbers, and so everybody's walking around trying to find the places they need to get to. They've got 20 minutes to get as many as they can. And the main audio content of this recorded in London was, I'm sorry, I'm very, very sorry. And that's because everyone's trying to move through a big crowd. That is the main experience, is walking through. So we can analyze that with reinforcement learning and do a lot. We've got a lot of a journey to go with this, but here's the eye tracking. And I have to say, like more than 90% of the time, people are looking at faces. Even in a scenario like this where you're walking around, they're looking at, you can see a little bit here, they're tracking people's faces and taking in as much as they can from the people. So it is not that people shift off. What I'll show you now is trackers. So we took 100 ultra wideband tracking systems, put them in those hats, and that meant then we could recreate the virtual art gallery here. And with the ultra wideband tracking, we could have everyone lined up, ready to go into the gallery, and then record as each of these 100 people make their way through the environment. And it's this data that's really valuable. This is the data that's going to be able to get us to patterns. So I'm just going to jump because we did a lot of different things there. We looked at navigation, we looked at exploration, and then we got people up. This must be the next one. Yeah, here we are. We got people outside the environment because it was under our control. If it was a real art gallery, it'd be quite hard to just go in and take sledgehammers and knock down walls. So we opened up the space and made it huge and looked at evacuation and crowd gathering and all sorts of things that I won't talk about now. And we found, here's some pictures from our cameras we're analyzing, and we're finding patterns to do with stress. So people who reported being more stressed occupied less space in that gallery. We have a lot to do with that data. In the last 5 minutes, I'm going to shift gear. I'm going to talk about cities where I've got a lot of data to new work we did on the ocean where we've only just finished collecting it. Here's my slide from earlier about the world's best navigators. With all that data, what you can't do then is analyze people from very small places because there's only a few people. And there's some of these places in the world come with incredible traditions in terms of navigation. One of those countries is the Marshall Islands. I've shown a picture on the top there of the globe where the Marshall Islands are. I wonder if anyone in the room's ever heard of the Marshall Islands. You may have if you read books about navigation, because this is an artifact from the Marshall Islands. So hold up. And you can see some children there. This is what's known as a Marshallese stick chart. I'll actually hand it out to Paula. Have a look. So this is an artifact. That one is a copy of the one in the image here, which is held in a museum. And it's pieces of stick with little cowrie shells attached to it. In this one, it's got them labeled. One of those labels says Bikini. And Bikini is a famous atoll because of the swimwear that's now popularized, because the United States government blew up pretty much half of the Bikini Atoll. It has a huge concrete dome to stop radiation leaking out of it. And it substantially affected the other bit of this photograph, which is the Marshallese sailors. Marshallese became one of the really most impressive seafaring nations in the Pacific. So expert navigators from other nations in the Polynesian and the Micronesian areas would come to the Marshall Islands to learn in their history. Now that artifact there, it's not a Euclidean map of space, but it is a map of space. It's a fantastic learning aid that that may well go back thousands of years to the ancient navigators there. It shows the connection between the islands, but what's really important, it shows the swells, the waves running across them. And it is those waves the Marshallese would learn from if they had been designated as a navigator from the age of 5. And in this photograph, here's the Marshall Islands again, shown top left. There's all the different islands. There's about 11,000 people that live in the Marshall Islands. And on the bottom left of that photograph is me in a blue top, next to some very important people for me in my life now. On my left in the photograph is Maria Ahmed, who sent me an email one day to say, would you like to do some research? I'm living in the Marshall Islands. I've met this man called Alson. Alson is the man standing next to me, covered in tattoos. He's standing behind his NGO, which is called the Canoes of the Marshall Islands. And Alson Kellen is the last apprentice navigator of the Marshall Islands, who's taken part in studies. He's a published scientific author, and next to him is the world-leading expert on navigation in the Marshall Islands, Professor Joe Gentz from the University of Hawaii. So 2 years back, I went out to discuss what we might do as a team. And what we decided to do only a month ago was to sail a yacht from one island, the island of Majuro, to another island, the island of Aur. And what you cannot do currently, because of chiefly permission, is to actually navigate. The scientific experiment we'd love to do is navigate from this island to the other one and record that. Not on the cards. So we had to come up with another way to do this. And the idea we came up with, rather than sitting on one of those traditional canoes, which last time they did it, somebody fell off and had to be rescued, why not use a luxury trimaran as part of our research? So rather than going out in London and testing taxi drivers, we were able to very fortunately engage with the indigenous community through the canoes of the Marshall Islands and recruit our team in this photograph. So you can see me, you can see Maria with the sunglasses. Next to me on my right are Clancy, Taika, and Ken Daniel. These two indigenous sailors from the Marshlands, they're young. They're like in their 20s and 30s, but they spent their entire life at sea. Like these guys, Clancy, who's got the hat on, is the champion sailor for the last 5 years. He's the national sailing champion. Ken's father is a famous canoe builder. So they come with this great heritage. On the further side, we have the only qualified anthropologist from the Marshall Islands, Geraldine, and somebody else there on the other right side, Pablo Fernandez Velasco, who came out as part of the Stirling Center of Place and Memory that I'm standing now. Behind them are two very important people that we could not have done this without, which was the ship's captain and the first mate, Ben Vroom, and Ari, who as a team were able to actually do the navigation that we're able to take this boat. So I'm going to wrap up. It's only got a few minutes and just show you some. It's like now moving to holiday snaps of a research experiment, but that is a genuine view off the back of the boat. Here's another view. Here, if I play, it should show you the footage of what it's like being on that boat. It's just like being on your honeymoon. It's an amazing experience being out on this luxury yacht, incredibly wonderful. The sky is incredible. The sea around you is incredible. And here's another one of footage of this. There's a, the rainbow in the sky at this point. It's incredible. Here's another movie of Clancy sitting on the edge. This is what life is like when you're doing this research, just to immerse you a little bit from a video. And you can't, like, it can show you all this, but actually being on that boat completely changed my experience. And there's Pablo doing something very important, eating food whilst traveling there on the boat. But it felt like, and Pablo can say, it felt like you're on a honeymoon because like the sun is setting. This is incredibly beautiful. It's one of the most stressful experiences of my scientific career because I'm doing that a lot of the time. I'm not looking at the view. I'm trying to fiddle with a highly expensive accelerometer tracker on the boat. We turned this yacht into a giant wave measuring device. We spent most of our time filling in clipboard surveys about how we're feeling and where we thought we were. But on our journey, we made it to the atoll of Aur. So that little white dot in the corner, that's us. That little white dot, that's us moored up on the atoll of Aur. On the atoll, we met the community there, delivered supplies. Here's Ken making judgments about space. Here's Clancy making judgments. On the way back, we recorded from Pablo's brain. It was so rough, we were not able to leave the cabin in the boat. But here is Pablo's brain activity. So we're able to record for hours on that boat And the small waves are his brain, but what was exciting was the bottom waves there are the accelerometer on his body. So you could see his whole body rising and falling with these waves and making judgments about the space using that. Here's some data from me. This is the first time I'm ever showing this data. What we're really at the heart of this project is a GPS trail, which I'm not showing you. It's not yet processed. But alongside the real GPS position from the satellite, we have my internal estimate of where at midnight, this is when this was taken, I was getting out of bed, Hugo, fill in this form, midnight, where did I think I was? What's my confidence in where I am? Which way am I facing? Where are the swell waves coming from that the Marshallese use? How confident am I about them? And then questions about how I feel and what do I know? What information am I using? And it's not just me reporting that, but the indigenous navigators. And one of the key results we have so far we're looking into is that for me and others, we're just thinking we're there. It's going to be there. But the indigenous sailors, they knew something was wrong. Like the boat on purpose, the captain was in charge. He went beyond. He didn't do what he was supposed to do. He was a bit sneaky. And they've lived their whole life on the sea. So their estimates should be better. But we will have to quantify that just the way we did the taxi driver data. It will take some time and put it into a computational model. So that's a wrap up. Here's lots of people that have made this possible, including particularly Pablo Fernandez Velasco across a lot of this, and the funders who've made it possible, all the direct funders, and then the universities that now have to stop up funders and donors to that. So a huge thank you to all those people who made it possible, and the donors for supplies to the Island of Hour who provided through experiment.com as well. And that's a wrap. So thank you very much for listening.